Hello everyone, and welcome back to the overflowing of the like button. Do it. Seriously, thank you. And in this episode, what we're going to do is actually go to something really cool, and that is live disassembly of memory. What are we actually gonna do? We're going to scan executable regions of memory, the actual code for references to global variables. And we're going to find those global variables, and we are then be able to search those global variables for our memory values. So just to recap, in the last episode, what we did is basically created this kind of a pointer map, which allows us to find all the offsets, like these little links between various memory addresses, so we can actually find the values that we search for. And in this episode, what we're gonna do is go into something called disassembly. And what do I mean by that? Our goal is to find global state inside the main function when it's being read. So for instance, it could be this particular part of the code. We save the address of global state into a GS variable, which would probably be like in some kind of register. So it's going to read the global state, which is right here. It's going to read it and save the address to this GS variable. And the way it's done in code is not by actually reading the address. Let's assume this particular instruction, this is read instruction called load effective address, and it reads the address into a particular register, and it reads this particular address. So let's assume this is our global state. So it's going to read it from this address, but it actually doesn't indicate in the instruction itself that it's this address. When the code is compiled, the program doesn't actually know the absolute address of the global state. What it knows instead is the distance to the global state from that particular instruction. So right here, the load effective address reads at this offset from this instruction, and it ends up with this address. And I can demonstrate it right now if I open LLDB and print void. The way it's actually done is slightly different. You take this offset and add the address of the next instruction, and you get this address, which is right this one. And this is basically how the absolute address of the variable is calculated. And basically what we're gonna do is go ahead, go through the code, find all these load instructions, and we're going to find the absolute addresses of all the variables that are being read. And we're going to find them, and in the next episode, we're gonna link everything together so we can scan really effectively for all our values. So without anything further ado, let's get started. What we're gonna do is create a so-called module. We are gonna call it Disassembler because it's going to be a disassembly module, and it's going to be a structured disassembler, which is going to have a map, which is going to be a B-tree map. It's going to map a particular instruction at a particular address to a particular global variable. So it's going to be an address to an address. And just like with the pointer map, multiple instructions can point to the same global variable. So we will need to be wary of that in the future episodes. And it's going to have a derived default, and the implementation is going to be the same reset function. We will do something about it later on. Self.map.clear. Then we're gonna have this function called collect globals. It's just going to be the do work function. Gonna have a mutable self, and it's going to take. We're gonna figure out what it's gonna take, but it's gonna result in nothing. And we need to fix up some imports. We're going to use memflow size and address. We're definitely gonna use size. We're gonna use memflow bin32 error. And yeah, so what we need to do is go through each module of the program, go through the executable regions of those modules, and then disassemble that code, and then be able to do it. And first of all, how are we gonna disassemble it? Well, we're actually gonna use a really awesome crate called iced x86. It's going to be iced x86, and it's a version 1.9.1. And we're gonna use the iced disassembler to disassemble the instructions. It will use a decoder, going to use decoder options. That's it. We need to walk through those modules, so we need to somehow parse those modules and know what's inside them, know the actual executable regions of the module. So for that, we're going to use PE-Lite, and that's going to be PE-Lite 0.9. For this, we'll need virtual memory object. And also we need to get the module, so we actually need the process. And the process has within itself the virtual memory object. So we're gonna take process, a mutable reference to a Win32 process, and we need to pass the type to the process, what kind of virtual memory object it is. And there are two ways to do it. In the previous episodes, what I would do is create a new generic variable, v implements virtual memory. But I recently found out a really cool way to do it in Rust. We are going to omit the generic type, and instead of the type, we're going to use implement virtual memory. And that's it. You don't need generic types. It makes the thing look much, much cleaner, in my opinion. And we're going to use memflow memory, virtual memory, and virtual read data. Definitely we're going to use that. We're going to use PLite, P-file, and what we're going to do is we're going to start with module list, and we're going to iterate through those modules for m in modules into here, and we're going to read the header of the module. So we're going to use create right here a zeroed header with 128 kilobytes of data. I found that enough for our purposes. Going to be process virtual memory, virtual read raw into. We're going to read at the base address of the module. That's where the header resides all the time. And we're going to read into image, and we're going to accept partial result in this case. And yeah, and we're going to create a so-called p file equals p file from bytes, and it's going to take the image. And we need to map the error of the PLite into our own error. So it's going to be map error, fail to parse header. There we go. And now we're going to iterate through sections which are like .text, .data. If you like use GDB info files, right here you have every different section, which is like .text, .read-only data, and like we're gonna iterate through all these sections, and is going to be in p file .section headers function, and we're gonna create an iterator, and we're actually gonna filter out. We're going to filter out just the executable sections, and it's going to be checking section characteristics to check for image scn count code not equal 0 is a particular flag which value is actually constant image scn code if it equals 0x20. We check for that, and every single section that matches these characteristics is going to be our executable section, and that's it. And we iterate for that, and now we're inside a section. So we're going to create the starting and ending bounds. We're going to use U64 virtual address. Actually, let's go full screen with this. As U64 and the engine address, and equals start plus section virtual size as U64. Now what we need to do is go from start to end by some certain chunk, which we have done countless times, and then disassemble each of those bits very, very well and just roll, as they say. So it's going to be, we're going to define a chunk size. It's going to be, let's say, 2 megabytes. We're going to create bytes. Yeah, bytes is going to work. 0. And we're going to take chunk size plus we're going to give a little bit of overflowing And single instruction shouldn't exceed 15 bytes, but let's just give it, we're gonna give 32 bytes just for good measure, and it's gonna be good. Yeah, we're going to iterate by that size chunk from start to end for address in start to end dot step by chunk size. We're going to create let end equals address. We're going to take the minimum actually. Minimum of end and address plus chunk size. So now we basically have the ending address of, and we're going to read it now. The address into converted into address. And we're actually gonna just read to the full buffer. And we're gonna call the disassembler and we're gonna disassemble as long as we don't overcross the ending barrier. We're gonna keep disassembling because we don't want to disassemble the same instruction twice. And we're gonna read, we're gonna accept partial results. So address actually is going to be equal. So basically what we did, we define address, which is going to be the maximum of address, and the current end, which is going to be the address of the last instruction we processed, so that we don't process the same instruction twice, and we also keep working in the chunk sizes with that little tiny bit of buffer allowed. And it's going to allow us to go create a decoder, which is decoder. And we're going to take the bits, we're going to take the bytes and no decoder options. Actually, we're going to set decoder, set IP address. I'm going to iterate what we need. We need the instruction pointer and we need an address from the decoder. Decoder dot into iterator. Now we're going to inspect it first of all. We need to update the cur end. Basically, cur end equals I dot IP dot enter. But we need to first filter it out so that I dot IP is less than ending address. Then we inspect it and then we apply the current end equals the instruction pointer plus I.len. Now we have all the instructions that are less than the ending address. Now we need to filter out particularly the load instructions, which are these, load effective address. We need to filter out which of these are load instructions. They have a so-called relative operand, and we need to take the instructions which have a relative operand. But we also need to make sure that those instructions are actually the load instructions or like write instructions, not the call instructions, because they're like call or like jump, which is somewhere right here, jump. They are also relative instructions, which have a relative operand. So we need to filter out only the load instructions, which have a relative operand. So it's going to be filter I.is IP rel memory operand. And also, we're going to check the branch target. Make sure that the branch target is nothing, is a null pointer. Then we basically have our instruction. It uses relative address and is also not a branch. And we're going to map it i.ip.into. We take the instruction address as the first address, and we're going to take the address which it points to. It's going to be i.ip rel memory address into. And what we're gonna do is we're just gonna do self.map.insert IP and address. That's all, really. So what we need to do is define the module. It's going to be disasm, and we're gonna use disasm. And let's see what errors we have. Right, we've got 3 errors. We cannot find the trait. We cannot find the B-tree map. Yeah. So we need to use std collections B-tree map. We need to use memflow 32 process. And the memory doesn't have the Y capitalized. Also, we need to use as What do you mean constant is never used? What the hell is wrong with you? Oh, because we never use the code. Of course. So what we're gonna do, we're gonna disassemble all the instructions, we're gonna create that map, and we're going to find which instructions point to our global state, which is this particular address. So we're just gonna do it at the very start. Really, I don't really care. We're just gonna do it let mut disasm equals disasm default. I'm gonna do disasm dot collect globals. It's gonna take the process, and what we're gonna do is we need to access the map, which is going to be this function. It's a getter method, and it's going to be self.map. So we're gonna do for I and O in disasm.map, disasm map iterator, and we're going to filter out whenever the output equals our instruction, which is right here, dot into. And that's about it. We're going to call it instruction global points to this. Going to be instruction global. And this doesn't work. Yeah. Here we go. Now this works. Did it work? Doesn't seem like it did. We've got very few globals, actually. Huh. Now it worked. Alright. We just had a tiny bit of issue, which is really understandable. We had a really tiny issue of the code being paged out over the time we were writing the code. So it actually works right here, as you can see. We have this. We have this particular instruction pointing to this particular address, which is this one. I could disassemble the instruction, but like we will merge these parts together. So basically, what we did in this episode, we wrote a disassembler. What it does, it goes through every single module in the code. It goes through each section of the module, finds whichever section is executable. Then what it does, it goes chunk by chunk through that section. You know what? We can simplify it a little bit because I think it's confusing. Address equals start. So we go by chunk size, and it's going to be file. Then we go and we get the thing, and what we do, and we take the address. And we're gonna do, at this point, we're gonna do address plus equals chunk size as U64. There we go. What we basically did then created this while loop, which tries to go by chunk size and disassemble each instruction one by one. Right here, we ensure that there is absolutely no overlap between the instructions, that they're not disassembled twice, for instance. And that we don't start disassembling in the middle of some instruction as well. That's also a really important thing to check. So we have this kind of for loop type of thing. And then what we do is we just insert into the map whenever we find which instruction uses IP relative memory and is not a branch call jump. And what this line does is make sure we do not overflow the limit. And basically, that's it. We create a decoder. We go through each instruction. We find instructions which are interesting to us. We add them to the map. And then we go ahead and we go through the instructions and find whichever instruction points to our global state, which is right here. And that's it. Basically, that's what we did in this episode. And I think we're starting to converge towards something really, really incredible. And in the next episode, we're gonna match everything right here together. All these three parts of value scanner, pointer map, and the disassembler. We're going to merge them together into a really beautiful offset scanner that we can use then, like, we're gonna search for a variable and we're gonna build a map back from, like, we're gonna list, oh, these particular code segments, they point towards your value, which you're looking for. And that's what we're gonna do in the next episode. It's gonna be really, really awesome. So yeah, thank you very much for watching. Pop down in the comments below what you think of this video and what would you like to see next. Don't forget to smash that like button, overflow that like button, hit subscribe for more videos like this, and I'll see you next episode. My name was Heap, yours wasn't defined. See ya.